Welcome to section 6.3, vectors in a plane. Let's get started. A vector is a quantity that has both magnitude and direction. An example of that is a ball that's flying through the air. It has a certain speed. It also has a particular direction it's going. The speed and the direction are the velocity of the ball. Velocity is a vector because it has those two things. It has a magnitude and a direction. Vectors are used to represent velocity, force, tension, and some other quantities. So let's go ahead and talk about how to calculate them. All right, so a quantity that has magnitude and direction, or vector, is represented by a directed line segment. We're going to call that PQ. PQ has an initial point P and a terminal point Q. And what we can see here is for our directed line segment, we're starting at P and we are going towards Q. This is going to give us a direction our vector is moving in. For notation, vector V is PQ. Notice we have the arrow above showing they have a directed line segment. And it's going to contain the set of all directed line segments of the length PQ, which are parallel to PQ. So what that means is we could have several different vectors represented by one vector if they have the same direction and they have the same magnitude. As an example of that, we could say that vectors u and v are going to be equal, meaning they are the same, if they are parallel and have the same length or magnitude. So we can see vector v going down at a certain angle for a certain length. Vector u is parallel to that, so v and u are actually the same vector, just translated in a different space. A vector with initial point 0, 0 is in standard position, and it's represented by its terminal point u1 and u2. So visually what that means is we're starting at our origin, and we are going towards u1, u2, and this terminal point is going to represent a lot of information for us. What we can say further, if our vector is not starting in standard position, so we have something in space here where we have P not at 0, 0 and Q also not at 0, 0, then what we're going to do is translate this back into standard position by finding what we call a component form. So if we have a vector with initial point P and terminal point Q, the component form is going to be Q1 minus P1 and Q2 minus P2. And notice that we have some angle brackets here. These are going to signify that we have a vector, whereas parentheses would signify a point. So make sure when you're talking about a vector, you're always using those angled brackets. We can also use our points P and Q to help us identify the magnitude of our vector or the length. So in order to do that, we have the following formula, where we have the magnitude of V is equal to the square root of Q1 minus P1 squared plus Q2 minus P2 squared. Again, we have some notation here that's a little weird. We have the double absolute value, which again is talking about our magnitude. And then don't forget that your angle brackets are what we use to signify a vector. So once again, just kind of recap, if we have something starting at the origin, then we have a vector in standard position. If it's kind of out in space and we want to translate it back into standard position, then what we do is we find our component form, which is Q1 minus P1 and then Q2 minus P2. So it's always terminal minus initial point. And then we can take that same kind of process and use it to help us find our magnitude by taking the square root of our component form, or the square root of Q1 minus P1 squared plus Q2 minus P2 squared. Let's go ahead and apply this in an example here. We want to find the component form and the magnitude for a vector with initial point at 3, negative 2, and terminal point at negative 1, 1. All right, so if we look at those points and think about them as vectors, we can translate point into P1 and P2, which would be 3, negative 2. And we can also translate point Q into Q1 and Q2, which would be negative 1, comma 1. If we want to go ahead and use these to find our component form for our vector, we're going to be subtracting appropriate components. So to find V1, my x coordinate, we're going to do negative 1 minus 3, which is again Q1 minus P1, getting us negative 4. And then to find our V2, which will be your y component, we're going to do 1 minus a negative 2, which ends up being 3. So now that I have the appropriate values, what I can go ahead and do is write this as a vector using my component form. We have V1, V2 is the vector negative 4, 3. Again, don't forget we have our angled brackets there. And then to go ahead and find our magnitude, if we do the same process, we have again Q1 minus P1, which is at negative 4. So I have negative 4 squared, plus Q2 minus P2, which is our 3. That's why I have our 3 squared. And then when I simplify, I end up getting 5 as my magnitude or my length of my vector. To do vector addition visually, we have a very specific process because we have each vector having its own direction, its own magnitude. So if I want to add two vectors, u plus v, what I'm going to start with is I'm going to place the terminal point of v at the initial point of u. So visually, you can see that I have v, and when v stops, I then add u. My next step is I'm then going to draw a vector with the same terminal point as u and initial point as v. So what that means is I'm going to start from v and draw towards u. And you can see that my green vector now represents the vector of u plus v. So just to kind of recap here, I'm going to draw v. When v stops, I'm going to draw u. And then I'm going to connect the two, so initial point of v to the terminal point of u to finish getting my final vector. If I want to go ahead and subtract my vectors, again, we have a process to outline that. I'm going to begin by taking the initial point of v, and I'm going to line that up with the initial point of u. So what that looks like is we can see the two vectors are connected at their initial point. Then what we're going to do is we're going to draw for u minus v, we're going to draw an arrow going from the terminal point of v to the terminal point of u. So we're going to go again from v to u if I'm doing u minus v. And we can see my arrow signifies I'm going from v to u, and that again is u minus v. If I were to switch this and instead want to do v minus u, I'd have the same process, but my arrow would end up going the opposite direction. The scalar multiple of a vector is the product of a scalar, which is just a real number, times our vector. So a scalar is a number that has no dimensions or no units. It's just an integer value, usually. It could also be a fraction. So if we have an example here, let's say that I wanted to take the scalar of 3 times v. What I would do then is I'm going to have 3v, which is 3 times as long and the same direction as v. So visually, we can see that I have v. 3v is going to be going in the same direction, but it's now 3 times as long. If I instead wanted to multiply by something else, let's say that we multiply by a negative 1/2, this does two things. So the negative sign is going to make sure we're going in the opposite direction of v. The 1/2 is going to now make it half as long as v. So I can go ahead and look at my vectors here. And we can see that v was going in one direction. The negative sign is going to make my arrow go the opposite direction, and the 1/2 is going to make it half as long. One thing to point out here, when we're drawing these, they don't have to overlap, they just have to be parallel vectors. So I could have drawn this v anywhere I wanted to, as long as it was going the same direction, meaning it had the same angle of orientation. So I could take this and move it out a little bit if I wanted to. I could have it kind of starting at a different point, but as long as the vectors are in fact parallel and they have the right dimensions and direction, then we've done it correctly. A second way to write vectors instead of component form would be as a linear combination. And a linear combination uses what we call unit vectors. Unit vectors are vectors that go in a specific direction and have a magnitude of 1. So we have one in our x direction and one in our y direction. For the unit vector in our x direction, we call it I, and it is represented by the vector 1, 0. For the unit vector in our y direction, we're going to call it j, and it is represented by the vector 0, 1. So I and j are universal notation for the unit vector in the x direction or the y direction. And again, they are unit vectors because they have a magnitude of 1. So the way we're going to take these unit vectors and use them to write a linear combination is I'm going to take my component form and I'm going to add in an I and a j with the correct component. So I'm going to add in an I with my x component, and I'm going to add a j in with my y component. So you can see in our example here, I have a component form of negative 2, 5. Since negative 2 is our x component, I'm adding an I next to that. And since 5 is my y component, I'm adding a j. And then I'm adding them together. If it was a negative 5, then I'd be subtracting them. So I'm just putting the appropriate sign to represent the sign of the y value here. But we can see we have a component form that has been translated into a linear combination using our unit vectors I and j. We saw some visual adding and subtracting of vectors. The algebraic one is much more straightforward. So we can see for any two vectors, v being v1 and v2, and u being u1 and u2, if I want to add or subtract them, all I need to do is add or subtract corresponding components. So if I wanted to add my two vectors, u plus v, then I would take u1 plus v1, the two x components, and I would do u2 plus v2, which would be my two y components. If I instead want to subtract them, I do the same thing. I just do u1 minus v1 and then u2 minus v2. Let's go ahead and apply this. All right, so we have our two vectors v and u. V is the vector -1, 4, and u is the vector 0, 5. We're going to start by doing v minus u. So going off our formula, we're going to do v1 minus u1, and then v2 minus u2. If you look at our work here, you can see that I've done that. So I have v1 minus u1, and then v2 minus u2. And then when I simplify that, I get my vector of -1, 1. And notice for my final answer, I do have my angle brackets there. If I flip the order, if I do u minus v, then it would make sense that my answer would just be the exact opposite. So you can see the work there supporting that. My final answer is again going to be 1, 1. If I instead wanted to add them, I would do u1 plus v1 and then u2 plus v2. And we can see that when I've added them together, adding corresponding components together gets me my vector of -1, 9. If I want to multiply by a scalar, again, algebraically, a little more straightforward than graphically, I'm going to take that scalar value, which we call k, and I'll multiply by both of my components. So I multiply by v1 and also by v2. Looking at an example of multiplying by a scalar, we have a vectors v and u. If I wanted to find 4 times v, again, I'm going to take that scalar of 4 and multiply by both components of my vector. And we can see that when we've done that and simplified, you end up getting 12, 8 as your new vector. If I wanted to do 2 times u, again, I take that scalar of 2 and multiply by both components of u. And when I double both components, I end up getting 6 and 8. And then lastly, for -3v, again, we're going to multiply by this scalar of -3. And you can see that when we've done that correctly, we end up getting -9 and -6 as our final answer. We have a couple properties here to go over, pretty straightforward properties. If we have u plus v, the order of addition doesn't matter, so that's going to equal the same as v plus u. With our associative property here, we have u plus v plus w, so the way we group things is going to be the same as u plus v plus w. So I can add u and v together and then add w, or I could add v and w together and then add u, and we're going to get the same answer. U plus 0, which is a 0 vector, is going to be just u. And then lastly, u plus its opposite is going to end up just being 0. Our next set of properties now involve using a scalar. So if I'm multiplying things together, if I have c times d times u, d also being a scalar, I can multiply c and d together first and then multiply by my vector if I want to. So I can multiply u by a scalar and then a second scalar, or I can multiply both scalars together first and then multiply by my vector. Again, for my scalars c and d, I can add them and multiply by u, or I could do c times u plus d times u. I could also add vectors together and then multiply by my scalar, or multiply each vector by the scalar individually and and add the sum together. For my last one, u times scalar 1 is just going to be u times the scalar of 0 is going to be 0. And then for my last one, this one's kind of important. So if I want a magnitude of c times v, that's going to be the absolute value of c times the magnitude of v. Again, the reason here is the magnitude is always a distance. So if you had a negative scalar, you're still going to have a positive distance because distance is never a negative quantity. One more formula for you here. We have how to calculate a unit vector that's not one of our normal unit vectors, I or j. The general notation here is you take the vector itself and you divide it by its magnitude. You can see it written slightly differently over here. I have the fraction 1 over the magnitude times the actual vector itself. But my preferred notation is I'm going to take each component. So I have v1 divided by the magnitude and then v2 divided by the magnitude as well. All three of these are equally acceptable. I prefer this last one. And one thing to note here, this u is standing not for vector u, but for the unit vector. All right, for our first example of finding a unit vector, we're going to find a unit vector in the direction of -2, 5. In order to carry out our formula, we want to make sure we can correctly find our magnitude. And based off our formula for magnitude, we can see that it's going to be our v1 squared plus v2 squared. When I simplify that, I end up getting -2, 5 over radical 29. And this is perfectly acceptable to leave your answer like this, but again, I prefer to do it as component form for various reasons. And then when we do it in our component form, you can see that we have -2 over radical 29 and then 5 over radical 29. If we wanted to verify that this was in fact a unit vector, I could then find the magnitude of this vector and it should equal 1. And I'll let you guys go ahead and test that out to make sure this does in fact work. One more example of trying to find a unit vector. We're going to do it for our vector of -4, 4. Our first step is going to be to find the magnitude of our vector. And since it's already in component form, we can go ahead and use that to our advantage. So to find the magnitude, we have the square of our first component plus the square of our second component. If I simplify all of that, then I get radical 32. If I take this one step further and I simplify my denominator and I put it in component form, then what I see is I have negative 4 over 4 radical 2, and then 4 over 4 radical 2. And then for my last step, if I simplify and rationalize this expression, then what I get for my new unit vector in component form is negative radical 2 over 2, comma radical 2 over 2. The direction angle of our vector is the angle that's formed from the positive half of the x-axis and the ray along which our vector lies. So we have a visual here. We can see I have my x-axis and then I have my vector, and essentially I'm rotating counterclockwise to get to my actual vector. We have another example here where my vector is in the fourth quadrant, and I'm going to go again counterclockwise to get to that. And our formula to help us find that is just going to be tangent of theta is equal to y over x, where y is the y component of your vector, and then x is the x component of your vector. All right, for our example, we're going to go ahead and find the magnitude and the direction for our vector. Our vector this time is listed as a linear combination, so you're going to make sure you can correctly identify your components. My x component is going to be this negative 2, and my y component is going to be the 5, and end up because of the I and j associated with them. To plug them into my magnitude formula, I'm going to take, again, my components. So we have negative 2 squared plus 5 squared, giving us the square root of 29 as our magnitude. To find our direction, again, our formula was tangent of theta is equal to y over x. So we're going to go ahead and plug that in, and we get the tangent of theta is equal to 5 over negative 2. Because we were trying to find an angle here, we're going to finish solving this by taking the tangent inverse of our fraction. And then we're going to get a specific answer here. Your calculator is going to give you negative 68.2, but negative 68.2 is not actually correct. And the reason why it's not correct, if you think about the point negative 2 comma 5, and I graph that on my x and y axis, I'm going to get a point in my second quadrant. A negative 68.2 would end up being in my fourth quadrant. So it's telling me the equivalent angle, but because of the restrictions on our tangent inverse, it's not actually correct. So what I would end up doing, since I know it's going to be in the second quadrant, I can do 180 minus my 68.2, and I get 118 degrees. And that gets me in the correct quadrant where my point's going to be. So when we're trying to find this direction, we got to be careful. The angle you get has to match up the quadrant of your point. If not, then we have to be able to calculate correctly where our angle is supposed to be. All right, one final example of finding our magnitude and our direction. Again, we can see the vector isn't a linear combination form. So I can take my components, which are going to be negative 4 and negative 7, and plug them in to find my magnitude. And if we do that, then we get negative 4 squared plus negative 7 squared, which gets us the square root of 65. To find our direction, again, we have the tangent of theta is equal to y over x. I'm going to go ahead and plug those in, and we get the tangent of theta is equal to negative 7 over negative 4. To finish solving for an angle, we take the tangent inverse of both sides. And once again, we have to be careful here because our calculator is going to give us an answer here of 60.26. If I go ahead and graph my point, negative 4, negative 7, it's going to end up being in my third quadrant, whereas 60.26 is in my first quadrant. So 60.26 tells me how much to rotate, but I need to rotate that much from my second quadrant here, which means if I add 60.26 to 180, I get the correct angle, which is 240.26. So once again, we see that the angle we got when we solved with our calculator, 60.26, needs to be added to or needs to be accounted for correctly to finish getting the correct angle of rotation, which is 240.26. All right, that does it for our notes. Go ahead and get started on the homework, and good luck.